Now that we have understood what is R square as a measurement of the model, there is also another parameter called as an adjusted R square. This is something that we can manually calculate. Um, so what happens is when you try to add more and more input variables, your R square improves, so which is great news. But at some point in time, because of certain phenomena, your R square tends to unusually go high. Um, it gets inflated in the process. This happens perhaps many reasons, but one of the reasons why it happens is that the input variables which are supposed to be independent of each other sometimes tends to be correlated with each other. Now, we it's sometimes difficult to identify correlations between input variables. Now, even if we identify, certain things might be out of control. So this phenomena is called multicollinearity, where the input variables are correlated with each other. They tend to inflate your R square. So you may get an R square of 0.9 and you might be extremely happy that you have an excellent model in your hands. But in reality, it's probably an inflated number. Maybe it is more worth of 0.82 or 0.80. In order to identify that, there is a small adjustment to the calculation that is being done, called as the adjusted R square. Now, for sake of clarity, I have given the calculation here, which is nothing but 1 minus R square into number of samples minus 1 divided by number of samples minus number of input variables minus 1. I'm just going to park it for the moment. But when you do that, you get R square and adjusted R square. The idea is that R square and adjusted R square should be close to each other. If they are drifting apart, then it means there is an impact of multicollinearity. Let's hold that thought for a moment. Now, as part of our data set, we have 10 different input columns, one target variable. And so far, we just tried with one variable, which is miles per gallon with weight as an input. Now, supposing you have to add the second variable. Sometimes it's very difficult to decide which one to add next. You have 10 and you might add the second one. It may not be the best variable, but it may give you some outputs. You may add a third variable. Then you might wonder what happens if I remove the second variable and add third and fourth. So we may go all over the place. An alternate technique is go ahead and add all the variables and then start to eliminate one after the other. So remove the most unimportant, then the next unimportant, next unimportant, so on and so forth. Now while you do all of that, check with your R square or adjusted R square. Now fortunately, there is a function that does this for us, at least part of it. It's RFE, recursive feature elimination. So what we do is, we go ahead and create a model with all the input variables, give it to RFE and ask RFE, can you please identify all the critical variables and can you rank them? So let's go ahead and invoke RFE and see what it does. So I'm going to create another model. Len mod is equal to linear regression. Maybe I'll change the name to L RFE. I'm going to initialize RFE itself. RFE mod is equal to RFE. You pass this model into this. So essentially RFE will call linear regression in a loop. So essentially we are passing the object here. Now I'm going to just put a value 1. 1 means identify top one variable, then put the remaining variables in some sequence order. RFE mod dot fit of x all y. So I'm using x all just for you to understand that I've used all my input variables. You can name it any way you want. Y is still 1. So we have run RFE. Now what I'm going to do is I'm going to get the important variables or the ranking from RFE. So this gives me the RFE. So if you map this and this, essentially I understand that weight is the most important variables. Now sometimes it's very difficult to read this, so I'm just going to create a quick little data frame, pass on two fields, your x all dot columns, comma RFE dot ranking. Okay, it creates a nice little data frame with two rows. The first row is nothing but the names of the columns. Second row is the ranking. So it's quite easy for us to understand how they are ranked. So you can see that weight is the first field, followed by AM, followed by QSEC, followed by TRAT. So it has given us the guidance, which is the top ranked variable, which is the next rank. So what we will do now is we'll attempt to add the input variables in this order and see where it takes us. Then when we add them, we will evaluate R square and adjusted R square. So let me refresh a new variable, len mod is equal to linear regression, x is equal to infile dot loc within bracket, all the rows. Let's start with the weight field, and y is equal to infile miles per gallon, len mod dot fit of x comma y, and let's do the predicted miles per gallon equal to len mod dot predict of x, and R2 score is equal to R2 score of y comma predicted miles per gallon. Let's also quickly calculate a few other variables. Length of y, this is to calculate your adjusted R square. X dot shape of 1, which is your number of input columns. This is basically the length of x dot columns, and adjusted R square is equal to 1 minus R square into n minus 1, which is number of samples minus 1, divided by n number of samples minus number of input columns minus 1. So this should do the trick. Now let's print R square and adjusted R2. So when I use weight as a model, that's my input data. My R square is 0.75, we already did that. Adjusted R square 0.74, which is pretty close to the number. Let's add our second field, which is the AM field, as per RFE. So I'm going to try this out. And now you can see my R square has not increased, but my adjusted R square seems to have taken a little bit of beating. Okay, fair enough. So let's try a few more variables before we discount AM. And when I add QSEC, oh, so that's a big jump from 0.75 to 0.84. My adjusted R square is also at 0.83. So let's go ahead and see if removing AM, if it improves or degrades our model. Looks like QSEC gave a much bigger jump. Okay, it seems to be, it has fallen down. So AM does seem to be contributing, but it's at a very small number. So let me retain it. But let me also go ahead and add one more field. Fourth one in this case is DRAT. You see that the adjusted R square dropped significantly while R square went up. So this is an issue of multicollinearity. Just for sake of completeness, let's add one more field, carb, and you can see that this has gone up to 0.86 while this has further separated out at 0.83. So this is not a good sign. So what it means is your R square is getting inflated. It looks like when we stopped here with these three fields, your R square and adjusted R square are pretty close to each other. Now, while accuracy is important for a model, you are also looking at predictability and consistency. In our opinion, keeping a simple model with fewer variables with good accuracy is much better than having too many input variables. Now, if I were to stop my model here with just three fields, three input columns out of 10, I'm able to explain a model, put together a model, which is very good, which has an excellent R square and adjusted R square. So anything more that we add wouldn't make a big difference to our model here.